And we're back for what will be our final installment in our derivative exploration, where we just discuss implicit differentiation. So if you watched the previous video, you should have come to hear me say when trying to define the derivative for a general exponential function, not base e, numerical base value, we had to perform some implicit differentiation, but I said that this video we would go into a little bit more depth regarding that. So implicit differentiation comes to fruition when we have this situation where y is defined implicitly. So as you can see in this equation here, right, y to the fourth plus xy equals x to the third minus x plus 2. Y is defined implicitly because the equation is not written in terms of x. Right, here we have y raised to the fourth power, and then we have the product of y with the x variable. Now, we technically have been doing implicit differentiation this entire time. However, we don't define it as such because, once again, our function is always written in terms of x. But if we were to derive this, right, we would take, well, we know that the derivative of x squared is 2x using the power rule. And normally we write y prime, I always like to write dy dx. Okay? Now what does dy dx mean? It means that, well, I took the derivative of y with respect to x, right? Because that was the variable that I was deriving. And normally we just leave it as such, right? And it becomes, once again, this common assumption. Well, what is the derivative of y? Think of it as, what is the derivative of x? Well, the derivative of x is just 1. The derivative of y is just 1. And it's, once again, something that we didn't necessarily need to state and something that we could just operate under this false pretense. Okay? So, once again, we have been doing implicit differentiation. It was just that when our equation was written as y equals, the derivative of y was simply 1 dy dx. So let's get into something a little bit more complex. Oh, what do you know? We've got a function right here. Let's do that one. Okay. So if I go to derive this with respect to x, okay, this is going to invoke the power rule. So y to the fourth is going to be 4y cubed times dy dx, right? I took the derivative of y, but with respect to x, which is why I need to write this. Now here, plus xy. X times y, so we're going to have a product rule situation, right? If I take the first function and multiply by the derivative of the second, the derivative of y is 1 dy dx. Plus the second function, y, times the derivative of x, which is 1. Now, we can sit here and say dx, okay? But it's a moot point, right? It's 1. And then the right-hand side of the equation follows as such. So if we wanted to collect our dy dx terms on the left side, right, because that's the derivative that we are taking, and start to transfer everything that's not over, right, we're left with 4y cubed plus x, that entire expression being multiplied by dy dx, which is equivalent to 3x squared minus 1 minus y. At this point, your algebra skills should be sharpened. So we would want to divide. And there is the derivative of our implicitly derived equation. All right. Let's take a look at this as it pertains to some trigonometry. Nothing crazy, but always good to look at. So let's say we had something like, take the derivative with respect to y of sine of y. Now look how this function is defined. Its input is written in terms of y. The derivative that we're taking, or the variable that we're taking the derivative with respect to, is y. So we can simply say that the derivative of sine of y is cosine of y because of this piece. However, if we had said the derivative with respect to x of sine of y, notice we're taking the derivative of a function defined in y with respect to a different variable. Therefore, we can take the derivative, cosine of y, but we also have to pay homage that we took the derivative of y with respect to x. Huge difference here. And last but not least, since this is the final video in our derivative saga, we might as well wrap it all up. Find the equation of a tangent line. Gotta love it, right? At p equals 1, 1. That's awesome. We got a point on the curve. Y to the fourth, plus xy equals x cubed minus x plus 2. This might be the point where you want to actually pause your video and see if you can accomplish, I guess, the mecca, right? Tangent line invokes derivatives. We're going to use the point slope formula at the end of it all, and then press play once you're done with your exploration. If you've continued to watch at this point, you'll come to find out, well, we just did the derivative of this implicitly defined function, and I believe that's what it was. Yep. So once again, we have our point, and where's the slope? Well, the slope is the same thing as the derivative. So we substitute these values in. 3 times 1 squared minus 1 minus 1 by 4, 1 cubed plus 1. 3 minus 2 is 1 over 5, and that represents the rate of change. Thus, our tangent line at the point 1, 1 of this implicitly defined curve is this linear function. And if you want to go ahead and turn that into slope-intercept form, algebra 1, you're a little hard away, but I will conclude at that point. Looking forward to our next topic, which will be curve sketching and boatloads of fun that relies a lot on what we just talked about in our, I think, 10-12 video segment. So, see you there.